Today we're going to talk about truth tables for logical operators. These, I expect you to memorize. It'll make your life a lot easier. Let's go over each in turn, starting with not P. So when P is true, not P is false. When P is false, not P is true. That's the only case in which not P is true, which should make sense. Not P is simply the opposite of P. Whatever P is, when it's true, its opposite is false, and when P is false, its opposite is true. The same, of course, goes for all the other variables you might put in there. Okay, P and Q. Here it gets a little longer, but it shouldn't be a whole lot more complicated. P and Q is true when P is true and Q is true. We're going to see that it is false when just one of them is false. Doesn't matter which one. And of course, P and Q is false when both P and Q are false. That should come as no surprise. If I tell you two false statements and stick them together, that doesn't make it a lie after all, or it doesn't make it anything other than a lie after all. So, always good when doing these truth tables to simply note the one that's different. In this case, that is the first line. All the others are false. As you memorize these, think true, false, 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 and you'll be able to solve your P and Q truth tables all the faster. Alright, P or Q is going to look pretty similar. First of all, it's true when both sides are true, and then we're going to see it's true when just P is true. It's true when just Q is true. And it is false only when both sides are false. So this is our odd row out, so to speak. You can memorize this truth table pretty simply as true, 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 false. Alright, if P then Q, this is definitely our most complicated truth table in the set, and it is by far the most important for you to not only memorize, but hopefully to understand why it is the way it is. Remember also, when we do arguments, that an argument takes the form of a conditional, and validity and the conditional are really working in the same way. So to understand validity, you'll need to understand the conditional, and vice versa. So, first of all, if P then Q, when the antecedent P is true and it leads to a true consequent Q, the whole conditional is true. When the antecedent P is true but leads to a false consequent, that falsifies the whole conditional. When P is false and Q is true, the conditional is true. And when they're both false, the conditional remains true. Now this throws a lot of students, so let's take each in turn. The first row, true and true and true, that one doesn't seem to bother anyone. Most people get that. You might say, if it is raining, then the ground is wet. And it is raining, and the ground is wet, so you're not very surprised that that conditional is true. But let's take a look at this line, probably the most important one. This is when a true antecedent leads to a false consequent. That's what makes the conditional false, and it's the only thing that makes it false. In the same way, the only thing that makes an argument invalid is when all true premises, like the antecedent of the conditional, lead to a false conclusion, like the consequent of a conditional. This is when you say something like, well, if it is raining and the ground is wet, well, it is in fact raining, and somehow it turns out the ground is not wet. That would invalidate your conditional. Maybe somebody has spread out a tarp under the entire area of the rain cloud, and it's in fact completely kept the ground from getting wet. That'd be a pretty odd situation, but it would invalidate your conditional. It would make it not true. Let's take a look, though, at what really throws students. These two lines. These are when the antecedent of the conditional is false, and it gets coded as true. This might strike you as a little arbitrary. Now, if you're not that interested in the why, you can of course simply memorize this truth table as true, false, true, true. Whether you are interested in the why or not, actually I do recommend you memorize it. But it's well worth thinking about why this truth table works the way it does. So let's think of a pretty mundane example. Let's say I have this rule: whenever it is sunny, I go for a walk. And we want to evaluate whether this accurately describes my life as a hard and fast rule as demanded by deductive logic. So let's translate that just a little ways closer to deductive logic. If it is sunny, then I go for a walk. Right? We can see now that this is if P then Q. It is sunny is P, I go for a walk is Q. And let's think about what happens if it's sunny and no walk. I decide one day, you know what, I'm just going to stay home even though it's sunny. Well, this disproves my conditional. It turns out it's not a logical rule that I go for a walk every time it's sunny. It turns out I make exceptions. So it's not much of a logical rule. Now, if it's not sunny, my rule stands. It doesn't matter whether I go for a walk or not. I can go for a walk in the rain, or a cloudy day, or at nighttime. That doesn't change my rule. I can stay at home, and it doesn't change my rule. Because it's not sunny. The question simply doesn't occur. One reason why our logic models human language this way is because it works particularly well for computer code. That is, after all, one of the main uses of this logical language is as the basis of coding things for computers. So if your computer code says something like, every time you press the Q button, it shows up on the screen, well, you've got a bug in your code if you press the Q button and it doesn't show up on your screen. That would be like the second line there, where P is true and Q is false. Ruins your conditional. But if you don't press the Q button, then whatever happens regarding your screen, there's no real problem with that rule. So in our version of logic, conditionals remain true unless they are proved false, just as arguments remain valid unless they are proved invalid. And that's simply the way we model truth in this language. It is important to remember that this is a model, and that, well, human language and real truth in the real world are a great deal more complicated than we capture in this language, and that's all right. The important thing for this class is for you to know what we are trying to capture with this language. Okay, the last one's a great deal easier, so let's take a look at it. P if and only if Q. Well, when P and Q are both true, the biconditional is true. If just one of them is false, the biconditional is false. But if they're both false, then our biconditional is true again. The biconditional, after all, tells us that the truth value of P matches the truth value of Q. It doesn't tell us anything about whether either one of them is true or false. It tells us, though, that one of them goes along with the other. If P is true, then so is Q. If Q is false, then so is P. If P is false, then so is Q. If Q is true, then so is P. The biconditional means they work together. They have the same truth value. And that is reflected in the truth table, which of course you can memorize pretty easily as true, false, false, true. All right, thanks for joining us.